Thank you, Matt. Today, I'm happy to present to you all on the topic of the DLL-defined digital devices in SIMPLIS. This is a project I've been working on for quite a while, and I'm excited that it finally made the release in version 8.4 here. For today's webinar, we're first going to review the current state of modeling digital content in SIMPLIS. We'll go over some of the advantages and limitations of each of the options. And then, having set the stage for where the DLL-defined digital devices fit in, we're going to cover some of the use cases and capabilities of this new feature. Next up, we'll touch on the system and licensing requirements, as well as some technical prerequisites. Then we'll do a small demo. We'll walk through the creation of a simple circuit element level DLL-defined digital device. We'll use the code and project generation tools to go basically from a specification all the way to a device that can be placed on a schematic and run inside of SIMPLIS. Having looked at an example there, we'll look at the outline of the life cycle of a DLL-defined digital device, what it's going to do during simulation, and some of the features that are available for the authors of the code used in it. And then finally, we are going to show off a DLL-defined digital device inside a power supply schematic. We're going to use a valley switching flyback that has sort of a state machine register hybrid combo to control where the switch turns on. So first off, yes, we're going to review the current state of modeling digital devices in SIMPLIS. And so we've got a couple of options. From the start, we had the classic SIMPLIS digital devices. These are analog representations of digital, and they're running inside of SIMPLIS's analog simulator. Starting with version 5.6, we released the advanced SIMPLIS digital devices. These are circuit element level devices that are in a true event-driven digital simulator. For pro and elite users, in version 7.2, we introduced the System Designer Symbol and Model Library. Now, these are a set of symbols and models that allow you to switch between the floating point representations and signed integer representations of these various symbols that they have in the library. So the floating point is modeled with the classic SIMPLIS digital gates, and the signed integer implementation is using the advanced digital. And finally, we have SIMPLIS VH. This is the add-on module that allows the co-simulation of Verilog Hdl using either Icarus, the open source Verilog simulator, or ModelSim from Mentor Graphics. Okay, first up, we have our classic SIMPLIS digital devices. Again, these are analog representation of digital parts, and they are modeled in the analog simulator. And if you've just got small amounts of digital content, these are an excellent selection. However, with large amounts of digital content, the simulator can tend to slow down with them. In addition, we have relatively limited support for primitives. There's gates, latches, and flip-flops, but for more complicated things, muxers, demuxers, or registers of any kind, you would have to assemble those out of the more primitive elements. And finally, the classic SIMPLIS digital devices allow the user to specify zero delay between a change in the input of the device and the resulting change in the output. This doesn't give SIMPLIS itself any particular issues, as it can handle instantaneous transitions, and there are times when you would actually want to use a zero delay. However, it allows users to create a digital circuit with zero delay, feeding back a portion of its output into its input, such that the circuit can essentially get caught in an infinite loop. The result is that SIMPLIS will do exactly what the user inadvertently asked it to, but it's unable to progress beyond a certain point in time because there is no time transpiring between the change in the input that causes the change in the output, which in turn causes a change in the output, which in turn causes a change in the output, on and on. And so the simulator appears to get stuck and it times out, and the users can have a very difficult time figuring out what's happening and why the simulation has appeared to have frozen. So to deal with some of those issues, in version 5.6, we released the SIMPLIS advanced digital devices. These are modeled in a true event-driven digital simulator inside of SIMPLIS. And if you've got large amounts of digital content, as our customers are increasingly including in their power supply designs, the advanced SIMPLIS digital devices will give you quite a significant speed increase. We also expanded the circuit elements that we support. We now give you registers, counters, arithmetic devices, sort of your adders, multipliers, subtractors, etc. And we fixed the issue with the zero delay output events. We do not permit zero delay output events with the SIMPLIS Advanced Digital Simulator. However, these devices are still pin-oriented, which means that if you've got a 32-bit bus, you're going to have 32 individual pins that you're going to end up wiring up. And this can lead to some very busy schematics. In addition, if you ever have to go back and make any changes to those devices, rewire them in any way, it can be quite a lot of work. Version 7.2 saw the System Designer model and symbol library show up. We took care of the issues with all the multiple pins. These are bus-oriented now symbols. They support, again, both the signed integer and the floating point implementations. And with the System Designer menu, you can select between those two modes. So you can use the integer mode to check your quantization effects, and then switch to the floating point mode using those classic digital gates, and you'll be able to run the pop and the AC analysis all in that one schematic. These are still circuit element oriented, and so if you've got a more complex device, or if you've got a fairly complex new algorithm that you're trying to check out, there's some extensive design that's required to get those working the way you'd like. SIMPLIS VH allows the co-simulation with Verilog Hdl. So either the open source Icarus simulator or ModelSim are supported, and you can use your production Verilog Hdl inside of SIMPLIS simulation. So all of your controller digital logic can be modeled inside of ModelSim using potentially even synthesizable code, and then SIMPLIS will handle the analog surround circuitry. The downside is it does require an external simulator. So again, you're going to need, you can start with the open source Icarus. Most of our customers doing serious work end up purchasing a ModelSim license to go along with that. And because of the fact that you're now having two simulators operating in lockstep, you have to pay close attention to where signals cross the Verilog and SIMPLIS boundaries, because the size of the time step that SIMPLIS can take is going to be affected by the fact that the Verilog simulators can't roll back in time. They can't rewind time. So SIMPLIS can't get any farther out ahead than the next signal it knows to send to Verilog. So if you've got a high frequency clock and you have that sent from SIMPLIS over to Verilog or Verilog back to SIMPLIS, you're going to end up with potentially a very slow simulation. I have a simulation schematic that if I swap out just one clock, moving it across the boundary, I can take that simulation from running in about 11 seconds and take it all the way up to, it takes 35 minutes when you make that boundary crossing. So paying close attention there is quite important. And I said this sets the stage now for the newest capability, which is our DLL-defined digital devices. So we've added the ability for you to write C or C++ to define the behavior of a digital device. These run inside the SIMPLIS advanced digital simulation engines and share basically the same advantages and limitations of everything else that runs in that engine. So first off, again, we do enforce a non-zero output delay for the reasons I mentioned before. And now is where we revisit the pop and AC question. Now, ultimately, it's dependent on the specific circuit and operating conditions. But in general, for digitally controlled systems, where the signals in the feedback loop are quantized into discrete levels, the pop and AC analysis is generally not applicable, because we do an extremely small perturbation of the injected signal during AC analysis, and that's typically not large enough to produce a control loop response when the signals are quantized out. So for circuits like those, they're typically better suited to the SIMPLIS multi-tone AC analysis, which is available in DVM. Now, the example I will show at the end of the webinar has digital content, the DLL, but it's outside of the feedback loop. And so that circuit actually does do our pop analysis. So it's not an instant disqualification by putting a DLL-defined digital device that you can't use POP, but it's going to be very dependent on where you put it in the schematic. What can we use the DLL-defined digital devices for? Well, we are using them internally now to implement and prototype new SIMPLIS circuit elements. So we're doing the proverbial eating our own dog food here. And I use this to mock up and then actually implement new devices that we may be adding to the SIMPLIS advanced digital engine. State machines are becoming increasingly popular with our customers, and implementing a state machine in a couple of lines of C code is, well, from a programmer's point of view, very, very, very superior to having to write it out with a counter and a series of lookup tables. You can get a new design or a new idea implemented using C a lot quicker than you would by having to flesh out all the circuit elements in there. Which leads us to, all right, you can prototype new digital control schemes, new digital ideas. So you can go from everything to, here's my small new prototype circuit element, all the way up to, here's potentially the model of an entire controller. Some of the things that the DLL-defined digital devices can do for you. We provide an automated project, symbol, and edit dialog generation routines. So by filling out a simple form, you can automatically create a skeleton Visual Studio project, including all the stubbed out code files, as well as once a project has been compiled, we will automatically create a symbol for you based on that, and an edit dialog that controls the user's interaction with the parameters that you've decided that they can edit. We have bus-oriented I/O. So like the system designer features, it is the symbols themselves use bus connectors, but also internally, you can read and write from these buses with built-in support for unsigned, 2's complement, and the binary offset encodings. And finally, parameterization. So all the devices are, the edit dialogs support parameterization for starters, and the last example will show that specifically. But also we support Monte Carlo and multi-step analysis. As I mentioned, with the Pro and Elite seats that System Designer used, also that enables multi-core support. So it takes a specific type of implementation that we will talk about later on, but we do support using your code-defined devices, DLL-defined digital devices, in the multi-core setup. So you can have multiple instances of your device running in multiple SIMPLIS processes at the same time. And if you use the provided routines, each individual instance will get the correct answers. I'll take a moment and just briefly touch here on our system and version requirements. So I'm kind of hinting at it. It requires SIMmetrix SIMPLIS Pro or Elite version 8.4 or later in order to run a schematic that has a DLL-defined digital device on it. Obviously, you're going to be writing some code, so you're going to need a C++ compiler toolchain. Internally, we use Visual Studio, and the projects that are automatically created are for Visual Studio. It is possible, if you're familiar with it, to take those generated code files and create a GCC makefile or do something else there. But we find that Visual Studio works quite well for us. For testing things out, the Community Edition works just fine. The free edition that Microsoft makes available to people. Licensing-wise, we use the Professional Edition internally here at SIMPLIS, but for students or folks who are just looking to test it out, the Community Edition will work just fine. So there's not necessarily a financial investment required there. And finally, we have the SIMPLIS Digital Development Kit, which is an optional download available from the website that has additional copies of the header files as well as the tutorial examples. So on the website, we have a full tutorial that shows you how to walk through some of the steps that we'll be glossing over today a little bit. We're not going to get too bogged down in actual lines of C code today, but all those example files are available in that development kit there. The header files are automatically created by the code generation tools, which is why this development kit is now optional. Okay, so now we would like to create an example. So we're going to use our code generation features to create a digital VCO. And we're going to do this voltage controlled oscillator in the following way. We're going to have two inputs. We're going to take a base frequency as a 32-bit unsigned integer and an exponent as a 4-bit unsigned integer, as well as a flag just to say that, you know, all my bits are ready. Sometimes when you're doing an A to D conversion, you end up needing this ready flag so that you don't get a bunch of spikes on your output. It will have the one output, which is the output signal, and it'll take a couple of different parameters: the initial condition, the output delay, and then the duty cycle. And the VCO should create a digital output signal whose frequency is defined as, you know, basically the base times 10 to the power of the exponent, and that will be the output frequency. So I'll go ahead and open up a schematic here. This is a schematic with a pre-filled spot for our new device here on the right, but basically it has a 1 kilohertz reference that we're comparing everything against. We have a digital signal source that's going to step us just through 0, 1, 2, 3, 2, 1, and back to 0. So it's just a relatively simple selector signal that it's outputting. And then we've got a lookup table for both our 32-bit base frequency and our 4-bit exponent. So I can show you quickly here. This basically just says that when my input is 0, I'm going to have an output of 1, input of 1, output of 20, input of 2, output of 300, input of 3, output of 4,000. So you can see that we're going to step things around both with the frequency here. Oops. Do that. And then the exponent. We're going to try and basically keep everything so that it's going to be stepping down. So we're going to do multiples essentially of that 1 kilohertz reference clock. So start off with in the thousands, then in the hundreds, then just down to 10, and then finally just multiplying it by 1. So in order to do this, we are going to create a C code DLL project definition. And I've gone ahead and created one here already. So I'll choose to open that up. This is demo 1. And this has pre-filled in the list of things that the user needs to provide. First off, your device needs a name. In this case, I gave it the variable frequency digital source name. It's going to need a version number. This is so you can keep track internally. In addition, we have the ability to actually create a full library. So you could support multiple versions of your design and device all in one library, either for archival purposes or if there's different revisions of the silicon. We have a list of parameters that we want the user to be able to modify. So in this case, we've got the initial condition, which is an unsigned integer, defaulting to 0. We've got our output delay, which is a double, default is 2 picoseconds. Then we've got a duty cycle. It's also a double, and its default is 1/2. Adding new parameters is just as easy as typing in the name you want, choosing the data type and its default value, and choosing add. Obviously, we don't want to have that one there, so I will remove it. And then the buses. We have the 3 input buses, the 32-bit base frequency, the 4-bit exponent, and then that sort of data ready signal, which is a 1-bit flag. These are all the input buses. Output buses is just the 1-bit output. Adding a new bus, just as simple. Name of the bus, the type of bus you want, what width you want, and choose add, and it'll put it in the right spot there. Again, we don't want this, so I will remove it. You can save the project, which just touches the project file, but you can also choose save and create C++ source. And when I choose that, at 1021, you'll see here, all of these files were created also at 1021. It goes into the directory specified by output directory. And we have now created all the files that are necessary for us to compile this Visual Studio project. So I'll go ahead and open up the project here in Visual Studio. And you'll see that we have, it closes, which is frustrating. We've got our header files, we've got source files automatically created, including one for each of the functions that the user needs to implement. There's a whole lot of things like your code goes here that shows you where you need to start providing some details. But this is pretty much ready to go. It has all our definitions for our input, our output, and for our parameters. So I'm going to go ahead and choose to build this. I'll choose a batch build. Select both of these. The default configurations are fine. SIMPLIS is a 32-bit process, so for the moment we'll be building 32-bit DLLs. When we do update SIMPLIS to be 64-bit, DLLs will need to be recompiled, just as a heads up, because 64-bit processes can't import 32-bit DLLs easily. So I'll choose to build these, and it'll run through all of this. Show us down here at the bottom that 2 of these succeeded, no failed, and none were skipped. So now I'm going to go back to SIMPLIS. I'll go ahead and I will close our project because we have done everything we needed with it. And so now I need to place the device on the schematic. So here I'll go choose the C code DLL menu, construct C code DLL symbol, and then I will navigate. So Visual Studio created a build directory. I'll go ahead and choose the release version of this. Created the project name of variable frequency digital source as we specified, and then I'll just go ahead and choose OK here. And you'll see that I have a symbol as an option, as well as when I place it here in the bottom left-hand corner, it lets me know that a symbol has been created for this. As you can see, we are short a ground pin here. So I'll double click on our device, and here we have, it's a relatively simple dialog, but it is the automatically created dialog. We have the ability to choose the initial condition, specify our delay, and then also change our duty cycle here. But what I will change from the defaults is the ground reference. I'm going to set that to yes. Again, we see down here the new symbol has been created, and we now have the ground pin here. This is technically simulatable, so I'll go ahead and run the simulation. And what you'll see, and I will just sort of undock this here. What you will see is that we have an output of 1/2, because we can compile everything for you, get everything ready to go, placeable and simulatable. But we have not implemented any of the features that put outputs onto your output buses there. So we haven't specified any values. And by default, if you don't specify a value, you get this 1/2, this X, which is unknown. But if we provide an initial conditions routine that takes the value from the user, from the dialog here, and sets the initial condition of the output appropriately, either to a 0 or 1, and then we specify an action routine that tells us what to do during simulation, then we can create the appropriate signals on the output. Now, what I've done is gone ahead and created a pre-baked version. So we'll construct a new DLL symbol from our known good here. Get the same looking symbol. We have the same issues, changing the ground reference. But this has been specified with the code that I wrote earlier to basically implement the values that we're talking about here. So we should end up with a 1 kilohertz, 2 kilohertz, 3 kilohertz, and 4 kilohertz signal as we move through the various selections of our base frequency and our exponent. And so now, bring up our waveform viewer. You'll see that instead of the flat out, we now have our 1 kilohertz matching. Here we've doubled it. Here we've tripled it. And down here, we've even quadrupled it where appropriate. And then we step back down as it goes. Again, it runs inside the advanced digital simulator, so it does have the advantage of being pretty speedy, especially on the project that's this small. So I'll go ahead and close this schematic. One second. And I had kind of briefly touched that there's some things that need to be done here, some features and some routines that you need to provide. So when SIMPLIS encounters a DLL-defined digital device in the netlist, there's a couple of things that happen. First off is the obvious, which is it's going to do a syntax check, make sure the right number of pins are connected, make sure that the parameters that the user has passed in fit the bare minimum of the specification of either integer, double, or unsigned integer. It's going to put all of those user-defined values into the newly created DLL-defined digital device instance. And then simulation is going to start. During simulation, there are 4 routines, and we saw them each having their own different function source file in the project here. But each one of those gets executed during the SIMPLIS run. So starters with setup. Every time that SIMPLIS loads a DLL-defined digital device, we call the setup routine. This gives us the opportunity to perform housekeeping and initialization activities. It's called once at the beginning of the SIMPLIS run. At this time, we do not know the logic or the state of any of the users or any of the input buses or pins of the device. And so only the user's input from the edit dialogues can be relied upon. When SIMPLIS is setting up this circuit, it'll call this setup function once, as I said, and you can do any number of tasks there, including getting the parameter values from the user, making sure that the user's passed in parameter values are logical and consistent. You can instantiate managed and unmanaged user storage, which we will talk about here in a bit. And you can get some pointers to any frequently accessed buses or pins if that's desired, or you can perform any initial or one-time calculations. So if there's something that is not going to change during the course of the simulation, doing that calculation during setup is a good time to do it. When setup is complete, SIMPLIS will begin, and it needs to find a starting operating point for the circuit. And so that's where the initial conditions routine comes in. So part of the device's specification is to provide a function that sets the initial conditions, which is the output values at t equals 0 of all of the device's outputs based on the parameters that the user has passed in via the netlist. So again, we don't have any information about the logic or the state of the input buses or pins. In this case, we passed in an IC parameter, so we would just write that to the output at t0. The function's called only once, and again, is called after the setup function. And it is called at the beginning of the SIMPLIS run if the SIMPLIS simulation starts at t0. Obviously, if you're starting from a snapshot or something where t0 is not the appropriate place to start, we won't use this routine. When SIMPLIS determines the circuit's initial operating condition, it'll call this function once. You can perform any additional calculations that you didn't take care of during setup. You need to assign all of the values of the output buses and pins at t0, again, based on that user input, so that we don't have the unknown x value. And finally, you can schedule any wake requests. So if you know that your device needs to wake up in 30 microseconds, you can ask SIMPLIS to wake your device up at that time. And all these wake requests are scheduled relative to t0. So that gets us through the initial conditions. At this point, SIMPLIS will have figured out what the operating condition is, and it's now going to start to actually simulate. So the action function, during simulation, SIMPLIS will wake the device, and it'll call the action function when one of 2 events occurs, basically. One or more of the device's input buses or pins change, or a wake request that I had mentioned earlier that was previously scheduled using the set scheduled wait function, either during initial conditions or during a previous call to the action function. If a wake request occurs, then the device will wake up as well. The action function will be told why it woke up, given a wake reason, and you can basically tailor your behavior accordingly. Perform calculations, set the device's output for that time step. Our documentation on the website has a pretty good explanation of the information that's available in the simulation context. Basically, what does your device know during the calls to any of these routines? The simulation time, what functions it can call, the reason the device was woken up. And during this action function, you can read or write values from buses or pins. You can detect edge events, positive edge, negative edge, or just generic edge. You can execute whatever calculations you need to do when it comes to figuring out what the output needs to be or should be in the future. And then you can assign values to output buses with again, with a non-zero delay. That action function will be called over and over again during simulation until simulation completes. After the simulation completes, SIMPLIS gives every device instance the opportunity to clean up after itself, basically. So if you've opened any files or allocated any memory using a different function, this is where you would clean up after that. It'll be called once at the end of the simulation, immediately before the program exits. And after the teardown function is called, SIMPLIS will basically free that library. So it decrements the reference count for that DLL. And it should not, at that time, try and read or write from any buses or pins or try and schedule any events. This is basically a teardown only. If you're using managed memory, that memory is already automatically deallocated for you. So most routines or most functions won't require a teardown function to be particularly detailed. Everything's pretty much handled when you're using the user storage. Speaking of user storage, because of the need to support analysis types that are multi-core enabled, again, this is the Monte Carlo and multi-step, as well as to give proper simulation results when SIMPLIS rejects time steps and appears to turn back time, we really, really, really discourage the use of global variables in the DLL scope. It's possible that you could luck out and not have a problem, but in general, you want to avoid using DLL scoped global variables for your code here. But we do also understand that, in essence, we need to have some scratch paper to keep some intermediate results on, or keep track of a previous state or a series of previous samples. And so to store this volatile information that isn't output, a DLL-defined device can allocate a chunk of memory managed by SIMPLIS, so it's always presented with the correct values that were assigned during the previous device wake event. So this, while it does have some computational overhead, always make sure that your code has the correct input so that it can make the correct determination of what its output needs to be. There's a simple little diagram here, and we're talking about what happens in your action function with the managed user data storage if our t right now, if our time is t equals n. So at t equals n, SIMPLIS has a copy of the memory from the previous time step, so t equals n minus 1, and it provides a copy of that to the action function. Now, your action function writes to that memory just like it would write to any other variable. Again, we're managing copies behind the scenes. So you can put in whatever, you've taken a new sample, so you're going to shuffle the samples so that the last 4 samples are representative of the actual last 4 samples here, and make your determinations, run your calculations, schedule your outputs. When your action function finishes, SIMPLIS then copies that managed user storage, that value for t equals n, and so when t equals n plus 1 pops up, we're now going to get the correct copy, which is representative of the values that the action function just wrote here. So if SIMPLIS later on has to reject a time step, they got too aggressive, missed an event on the analog side and has to roll back, for example, the correct values from t equals n minus 1, since we're keeping these copies, will be presented when t equals n comes around again, shall we say. So when we pull the Groundhog Day and have to relive that day, the correct values will be there so that your device doesn't get lost. There are things that you want to keep track of where you've got variables that are unknown at the time that you're writing the code. in terms of their value, but they don't change over the course of the simulation. And for that, we also have unmanaged user storage. So this does not keep copies, but for things like the parameter values that were passed in via the edit dialog, or any calculations that, or intermediate variables that are derived from those parameters that don't change during simulation, pointers to buses or pins, these sorts of things can be popped into your unmanaged user storage there, which you would deal with it at setup time typically. And in the unmanaged user storage, it doesn't keep a copy of it, so therefore it's more efficient, but you don't have to repeat those intermediate calculations every time the action function is called. So we've gone over now the sort of examples of the functions that you are going to need to define for your device, when they're called, and we have gone over some of the features that you have, writing to output buses, managed user storage. I'd like to show one last final schematic here, which is demonstrating a valley switching flyback. So this valley switching flyback, the primary switch turns on when the voltage across the switch is at the local minimum, also called a valley, of the resonant ringing, which is occurring in discontinuous mode operation. And in this example here, we've got a C-code DLL implementation of the algorithm that just determines which of those values are going to be triggering the switching. So we've created a subcomponent with a pretty little dialogue here that we'll go over here in a second, but deep underneath in here is just an automatically generated symbol from the CDLL. All the properties have been parameterized, showing again that we do support that parameterization, and they're being passed in from the custom symbol in the surrounding subschematic. But this is just a, underneath it is the auto-generated symbol. So this basically works. The controller itself is analog, and that is how we can go ahead and have a pop analysis run with this, is because the digital device is not in that feedback loop. It is looking at the feedback signal, and each of the 4 FBTH, these are feedback thresholds. So it basically divides the feedback signal. It can be in now 5 different regions, and these thresholds indicate which of those regions have been tripped. So that information goes into the DLL, and the DLL then is, as I mentioned, kind of the combination of a state machine and a register. It keeps track of the current value for the number of rings, basically which of those values we're going to use for the switching. But it also is a state machine that basically reacts to the feedback threshold signals and schedules the output accordingly. The parameters here, we need an initial condition. In this case, we've set it to 7. We're in a high line condition. We have a wake interval. So this is how often this device is going to wake up, take a look at the feedback threshold indicators, and schedule the output accordingly. This is the output delay. Again, it can't be 0. And then we have some minimums and maximums based on the line and load conditions. So if we're in minimum phase, then the minimum number of, or low line, sorry, condition, then the minimum number of rings is 1, maximum is 7. And then for the high line condition we're in now, minimum's 3 and the maximum is 9. In our algorithm, basically, I got handed a spec, that was basically this circuit with some information that said, okay, we need to have our device work in the following way. And we've created, Tom helped me create a pretty cool graphic here. It sort of shows, I'll undock this as well, what we want to be happening during our simulation. So again, we've divided our, let's zoom in here a little. We've divided our range, feedback range, into, there's 4 signals, so there's 5 sections. If we are in the minimum here, we want to set our ring count to max. If I'm in the feedback threshold, so that's section 1, we basically are just going to hold whatever the current count or the ring count is. we're going to leave it unchanged. When I start creeping up to the feedback threshold 2, I'm going to start decrementing. So every time the device wakes up, I'm going to decrement the count until it gets down to the minimum. And then if feedback 3 ever goes high, we should instantly go to the minimum. And if we're below all the thresholds, we should instantly go to the maximum. So that was the spec I got from Ray Piliakaitis, who did a great job putting together this circuit. And what we came up with for that was this schematic here, that when we simulate, oops, I'm gonna undock all of these. So when we simulate, we can see that, again, first off, this circuit did pop. The DLL was not in the feedback loop. And we see our operation here. So here's our feedback voltage. And it starts off in the range of, we're just going to hold it constant. So that's that feedback threshold 1 area. Our initial condition, if you'll recall, was 7. So we're hanging out at 7 for a while. Now we're starting to dip down with our feedback signal into the feedback threshold 0 area. And that's where we're incrementing now until we hit the maximum. So we can see it step up, and now we hit the maximum. We actually drop below feedback threshold 1 to threshold 0, which just says go to the maximum. So there aren't any changes here. And then finally, we start to see more of our responses to our transients. And we got a pretty big spike up here on our threshold voltage. So instantly, since we get to feedback 3 passed, we're going to drop our ring count to the minimum. And then as we work our way out here and settle back into steady state, you'll see that it tracks accordingly. We drop all the way down, so we go maximum, step down, now we're in a constant state. And you can see, so we'll zoom in here right at the beginning, where our count was 7. And so 1, 2, 3, 4, 5, 6, and then on the 7th one, that's where that switch turns on. And if we go up here, we'll see that we're going to asking for the maximum up here. So we will have seen that change now. 1, 2, 3, 4, 5, 6, 7. Here's our, we're in 8. So feedback threshold 8. On the 8th one, we drop. And over here, we're actually, the analog controller is saying, I understand the rings you want me to use, but we're not actually going to do that for now because I've got a better idea. But when it starts back up again, we'll see that we're down at our minimum, 1, 2, 3, and on. I am not certain exactly how I would implement that digital device in using circuit elements. It's pretty complicated, but even exceedingly well documented and white space formatted to be pretty, it only took about 150 lines, and that's literally a line count there, of C code in order to get that implemented. And it took me about an hour and a half to get it right. So I would have been staring at that schematic for quite a long time, just figuring out where I needed to go if I was trying to implement that with circuit elements. And so the advantages of using the DLL-defined digital device here is that you can prototype new ideas, check out new features, and again, create components that don't exist in our default library here, and very quickly get them on a schematic, testing, see if your idea works or not, without having to spend too much time basically testing the test, as it were, and making sure that your circuit that represents the logic is doing what it is. So if there's an issue with the overall performance, was it a problem of the thing I implemented, or was it a problem of the surround circuitry? You can get rid of a lot of that by speeding up your development tasks. And again, you've got the code. Our example on the website shows you can actually do step-by-step debugging of your code. So you can walk through it step by step as SIMPLIS executes. You can check out what your inputs are, what your outputs are, and watch as each line of code goes by and determine whether or not, all right, I'm getting the correct behavior out of my code here. Really easy to validate that. So if there's an issue, it must be with the surround circuitry. Likewise, you could find that your code has an error in it and you need to fix it. The tutorial on the website is it's very thorough. It steps through creating a counter with an increment. And it includes all of the customized code as well. So you can see the examples that we put together there with actual code, not just the stubbed out. So to recap, we went over current digital modeling options in SIMPLIS, set the stage for where these new DLL-defined digital devices show up, talked about the version requirements. We walked through our digital VCO there, talked about all of the functions that the users will need to provide in order to actually have output to their DLL-defined digital device. And then we walked through our valley switching with flyback example, where we used a DLL-defined digital device to provide input to the IC there and specify the appropriate number of negative slope zero crossings or valleys before we turn that switch back on. So I think we'll hand it back over to Matt now and see if there's any questions.
All right, thanks, John. Yeah, if anybody has any questions, please feel free to write them in at this time. As it stands right now, there are no questions.
Well, in that case, let me just take the time to say again, check out the documentation on the website. It does walk through that demonstration, including how to debug it in the live environment. And there's good documentation on each of the available functions that your code can call that are provided to you during each one of these routines that you're creating. And it gives you the information on, how do I get to what the current simulation time is? Basically, the sort of the nitty-grittier details of that code there. But the documentation is up on the website, and it's worth a look.
Thank you, John. We do have one question come in. Can printf be used with the DLL?
You can call printf. Where it actually ends up printing out, you might see in this SIMPLIS status window here. Yes, so I mean, you can call printf and it should, to the status window of the active thread is where you might see something. It's not the easiest approach to doing that, but it does show up. So I find that the live debugging is an easier way to do that, but to check out what they are. But yes, it can be used.
Okay. I guess there was an update to that question. They wonder if they could print a file, not printf.
Oh, sorry. Yeah, printf, the function in C is a formatted printing. fprintf to a file, sure, you can write any files you'd like. You don't have access inside of this DLL basically to anything other than what your DLL sees, but you could certainly write a log file. Anything that's basically available as a function inside of C or C++, you could probably use. I was tempted to put together a demo that actually went and downloaded something from the internet just to show that it could be done during the simulation, but it's kind of a gimmicky thing, so didn't have to go with that. But certainly you can open and manipulate files that you like. Again, you're going to want to be real careful if you're in a multi-threaded environment, because concurrent access to files is something that's going to be governed by the operating system. So if you've got 4 processes in parallel and they're all trying to open the same file name, you could get yourself into some issues there, but certainly you could print to a file.
Alrighty. Is it possible to online debug the library with Visual Studios open in parallel?
On the same local machine, sure. I don't know that, but basically you could have Visual Studio open, you attach it to the simplest process, and then it, if you've got a debug breakpoint set in your setup, initial conditions, action, or teardown function, then those breakpoints will be tripped and you'll be able to single step through the code there.
Right. And can this device be encrypted as normal?
I mean, the encryption handles netlists, and this is not a netlist. I would think that for most things, your DLL is not going to be telling anybody anything that they couldn't get from the datasheet when it's describing the device's operation. Since this is not, microcode that can be decompiled, this is not Verilog Hdl source code that can be turned into plain text and somebody could reverse engineer an actual product from that. This is just a behavioral description of the way the device works. One of the things you're going to run into is if you are saying that I want to have an encrypted file on my user's machine that then decrypts itself and is executed, that's exactly how viruses behave and Trojans. So you're going to run afoul of the end user's virus detection software, and it's going to look pretty nefarious when you try and do that. So no, these devices are not encrypted. But again, I think most of the time, the information that somebody's going to get by, and you don't want to hand out your debug tables, obviously, but just the release version of that DLL is nothing that you wouldn't be telling them in the data sheet describing how the device operates anyway. Okay. Ready. Anything else here?
All right, we got another one coming here. Okay. Can I use it to simulate the behavior of a DSP-controlled power supply?
I mean, you can create anything you want. We don't ship with any models of any processor cores or anything like that. So this is not a situation where you're going to be providing firmware and then we're executing that firmware. This is a situation where you're going to use C to describe the behavior of the device, and we'll compile into something that Simplist can read. So if you can write it, Simplist can run it, but it's not something, again, that you're going to be using a particular vendor's code generation tools to create, firmware or microcode for a microprocessor or a DSP. All right. Right. Okay, here we go. I was having a little trouble with the questions pane there. Can I change the next update time, or is the time between the function calls fixed? So these are the wake indicators. And when you request a wake up, that is something that you do on a relative basis during the action function. So you say, please wake me up, 1 microsecond from now or 10 picoseconds from now. And that is something that is parameterized. It's a function that you call. So it is not a fixed update schedule. We did implement the Dll-Defined digital device in that value switching flyback to have a consistent wake interval, but you could absolutely, if you programmed it that way, choose to have something that's a fixed, or excuse me, a flexible or variable wake up times. Do I have a plan to co-work with a vendor to develop a plant that can simulate a DSP-controlled PSU? Okay, we are, this particular product and feature does not do that at the moment. But if you have, again, a way to describe how that DSP is going to work, you can make that work with Simplist. Let's see. So we can't have time interrupt behavior as real DSP operation process. That I mean, using the debug version of a DLL, you can interrupt a Simplist run and hit pause on it. The downside is, again, that Simplist may tell you that we need to rewind time, and you may end up going through the same time step more than once. So that I would be concerned about that for using time interrupt behavior with a DSP type operation process. It's probably not impossible, but you'd be in a situation potentially where Simplist rolled back, and or if you're trying to hook it up to a DSP somehow with a USB cable or something, that device can't go backwards. So hopefully that answered the DSP question there. I'm not 100% sure, but I think that's what they were asking.
Alrighty, is there any more questions for today? Go ahead and give everybody got about 2 minutes left, so we'll give about a minute left. Alrighty, well, thank you, John. If there are no more questions, we're going to go ahead and wrap up the session. A few items to remember. A recording of this webinar will be available tomorrow on our training page, and that's www.simplis.com/training.